Hello dear friends, welcome to a lecture of vector calculus. In this lecture we shall study gradient of a scalar point function. We shall study also the operator del, and then we shall express the directional derivative of a scalar point function in terms of gradient of the scalar point function, and we will solve some problems on it. I have written here the expression earlier. Let suppose phi be continuously differentiable scalar point function, and we have studied the directional derivative of phi along any line with direction cosines L m n is having this expression. So, L dou phi by dou x plus m dou phi by dou y plus n dou phi by dou z is actually the directional derivative of phi along a line having direction cosines L m n. And this expression can be written as a dot product or scalar product of these two vectors. We know I bar, j bar, k bar or I j k simply we say are the unit vectors along the coordinate axis x, y and z. And how to perform their dot product of these two vectors, that is component wise, because I dot I is 1, j dot j is 1 and k dot k is 1. But I dot j, I dot k, j dot I etc. are the dot product of different unit vectors perpendicular to each other is 0, and thus this will be the dot product is, or if you consider the vector A as a1i plus a2j plus a3k and vector B as b1i plus b2j plus b3k, then their dot their dot product is vector A dot vector B is equal to a1 into b1, because I dot I is 1. So, that is I component into I component plus j component into j component a2 b2 plus k component into k component, that is k dot k is 1 and therefore it is a3 b3. So, this result is used here, and that gives L dou phi by dou x plus m into dou phi by dou y plus n into dou phi by dou z. So, thus this is the dot product or scalar product of these two vectors is the directional derivative of scalar point function phi along line having direction cosines L m n. But now here the first vector we shall see. What is the first vector? Li mj plus nk, and that is unit vector along the line. So, that we shall write and we will see how it is unit vector. The first vector on the RHS, that is Li plus mj plus nk is the unit vector along the line with direction cosines L m n. So, because what is the magnitude of this vector? The magnitude of Li plus mj plus nk is, by definition, it is the under root of sum of squares of ijk components, that is L square plus m square plus n square, and we know the sum of squares of the direction cosines is equal to 1. So, this expression is exactly equal to 1, and root 1 we consider as 1 as positive magnitude, and thus magnitude of this vector is 1. Therefore, it is a unit vector and it is in the direction of the same line, that line having direction cosines L m n. So, therefore, this is the unit vector along the line. And what about the second vector that we shall now define? This second vector we are going to define as gradient of the scalar point function phi. So, we write the definition of gradient of phi. Gradient of a scalar point function phi, or we write is defined. So, this is actually the definition we will consider. Gradient of a scalar point function phi is defined as grad phi, or defined as we will write the definition, and it is or first it is denoted by in short grad phi is denoted by and is defined by gradient phi. So, this is actually the definition we are writing. It is a definition of gradient of phi, and gradient of a scalar point function is denoted by this symbol grad phi and is defined by grad phi is I dou phi by dou x. We shall write is defined by gradient of phi is equal to, we write I j k unit vectors as first I dou phi by dou x plus j dou phi by dou y plus k dou phi by dou z. So, this is gradient phi, and this we shall remember as definition of gradient of phi. And with this now you see this is a vector, unit vector along the line, and therefore what is the expression for the direction derivative of a scalar point function phi? It is the dot product or scalar product of unit vector and gradient of phi. So, therefore the directional derivative is, and further we will consider this unit vector. Now, unit vector along the direction. So, suppose if this is the line having the direction cosines Lmn, then this will denote the unit vector. Therefore, the directional derivative is, now if we denote the unit vector along the line with direction cosines Lmn as a cap, then a cap is equal to Li or Il we can write plus Jm plus Km. So, same expression. Ijk we will write first, and the Li is same as Il, Mj is same as Jm, etc. So, this is a cap, and now this right side becomes, this is a cap into gradient of phi. What is a cap? A cap is unit vector, and that we have written. It is the unit vector. It is the unit vector, and we have denoted it by a cap, and therefore the directional derivative of a scalar point function phi along a line with the DCS element direction cosines. I shall write in short DCS Lmn is that is, this vector is a cap, unit vector. This is a notation for unit vector, we denote it by cap notation. So, a cap denotes unit vector, a cap along a, unit vector is a cap into or dot gradient phi. So, this is the expression for directional derivative. So, it is a cap into gradient of phi. So, this is another form of the result, or actually this means a cap dot gradient phi, where a cap is Li plus mj plus nk. And further, after defining this, the definition we have written for gradient of phi. Now we will define a differential operator, which is important, and denoted by del. That is the operator del. We define the operator del. Called del, or sometimes it may be called as nabla, by del is equal to I dou by dou x plus j dou by dou y plus k dou by dou z, where I, j, k are usual unit vectors along the coordinate axis. So, this is the definition for the operator del, which is important, because we will express the gradient. Further, we will define divergence curl of vector point functions in terms of this operator del, and therefore, what will be gradient? So, with this operator del, we will have the gradient. So, therefore, we have gradient of phi. Gradient phi, now see, this is defined as I dou phi by dou x, etc. Now here these are partial derivatives of phi with respect to x, y, z, and it can be written as I dou by dou x plus j dou by dou y plus k dou by dou z, and these are operated on phi. These are operated on phi. There is no symbol in this, but we have to write phi, and this means this is distributive. This operator is a distributive. It is partial differential operators, a vector in terms of vector, and I dou by dou x is operated on phi, means I dou phi by dou x, plus j dou by dou y operated on phi, means I j dou phi by dou y plus k dou phi by dou z. And what is this bracket? This bracket is del phi. So thus it is helpful to write this expression in short with this symbol del, and the expression for gradient phi becomes del phi. So thus we have first defined gradient phi, then we have defined this operator del, and we have expressed gradient phi in terms of the operator del, which is del phi, and the total differential can now be written as the differential d phi. So we can write, or we have, by a result on total differential, we have d phi is equal to phi is function of x, y, z, scalar function of x, y, z, and therefore we can write this as dou phi by dou x, partial derivative of phi with respect to x into differential of x, plus dou phi by dou y into partial differential of y, and plus dou phi by dou z into differential of z. So this we have studied in partial differentiation, how to write a total differential. So if that means if z is a function of x, y, then we write the total differential of z as dou f by dou x into dx plus dou f by dou y into dy, and similar to that it is extended for three variables x, y, and z. And now this expression can be written in the form as, we will write I dx plus j dy plus k dz, as the first vector and we take its scalar product or dot product with the another vector as I dou by dou x or dou phi by dou x plus j dou phi by dou y and plus k dou phi by dou z. Now see, the first vector we can write as dr bar. What is r? R will be the position vector of a point having coordinates x, y, z. So the first is dr bar. We will see how it is dr bar dot. And what is the second vector? It is I dou phi by dou x, etc. So this is exactly the gradient of phi. So this is gradient phi. Earlier we have defined this as gradient phi, and thus we have d phi is equal to dr dot gradient phi, where r bar is unit vector, not unit vector but the position vector of a point x, y, z having coordinates plus j, y plus k, z. So r is ix plus j, y plus k, z, and therefore what is dr bar? Dr bar is I dx, taking differential of this I dx plus j dy plus k dz, and therefore we have replaced this written this I dx plus j dy etc. as dr bar. So this is the total differential d phi, and similarly we can express the total differential for vector point function. Or further, this can be written as gradient phi is del phi, and therefore d phi is equal to dr dot del phi. So thus d phi is written in terms of this scalar product of these two vectors, and the gradient is written in terms of del. And similarly we write df bar, differential of a vector point function. Similarly, the differential of a vector point function is df bar, and that can also be written as dou f bar by dou x into dx plus dou f bar by dou y into dy plus dou f bar by dou z into dz. And again we can write this as I dx plus, we are purposefully writing these unit vectors as first, because while what is the del operator, in that operator we have to write I first and then the partial derivative of phi with respect to x. So therefore in each expression we are writing these unit vectors as first in the term. So j dy plus k dz, this is the first vector, and the second can be written as dot I dou f bar by dou x plus j dou f bar by, or yes, we can write this as and this f bar we write as separate. So that can be written as dou f bar by dou y or plus k dou f bar by dou z. And now the product of a scalar product of these two vectors will be exactly the same, but we instead writing this as this expression, we can express the same in the form dot I dou by dou x plus j dou by dou y plus k dou by dou z, and this is operated on f bar. This is operated on f bar. So which will be I dou f bar by dou x plus j dou f bar by dou y plus k dou f bar by dou z. And now this is, so first this dot product is performed and then it is operated on f bar. So this will be, first vector is dr and the second is del. So, dr dot del operated on f. So, this will be the expression for the differential of vector point function. So, thus we have defined gradient and the del operator, and we are expressing the results these in terms of the del operator. Now, we will solve some problems on it.